Okay, so welcome to the third week of the Chromatic Seminar. So, okay, everything seems to be all good. So today's talk is on, it's about Lazard's theorem and complex orientable cohomology theory, oriented cohomology theories. Okay, so right off the bat, uh, but yeah, I mean, I'll answer that. It's orientable cohomology theory. Right. So here's the plan. So there are two parts of the talk. So first would be like, so just like briefly talking about some introductory stuff. I'll talk about like although we have had a few couple of introductory talks, I'll define formal group laws, and then we'll get into the details of Lazard's theorem, and then we'll talk about complex oriented cohomology theorems, right? And so there are first two parts, and for the first part there are like two halves, and you can picture it this way. So first will be, so we'll introduce the Lazard ring, we'll talk a bit about formal group laws, and then we'll prove, and we'll go on to prove the theorem, right? And for the second part, as the title suggests, we'll talk about complex oriented cohomology theories and give a few examples and a non-example also possibly, right? And then I'll talk a bit about complex Buddhism, so that like it's a bit, the transition is smooth for the next stop, right? So, okay, before I begin, so maybe a few things that I would like to say, right? So, right off the bat, I assume that people know what a complex orientable cohomology theory is. It's like, so the Amartya spectral sequence, so that right. So if the on the E2 page, the Amartya spectral sequence degenerates at the E2 page, right? So what is the motivation? So the thing is that, again, we've had a few introductory sessions, but still let me kind of talk a bit about the premises. So the thing is that to every complex oriented cohomology theory, we'll see this, we can associate a formal group law over even cohomologies. So if we have so this is a complex oriented cohomology theory, we can associate FG formal group law, so I'll abbreviate it by FGL over even. Right. So, right. And sorry. So we have a universal example of a formal group law. So what do I mean by, so why will we talk about Lazard theorem and stuff? Like what is the premise? What are the premises? So we have a universal example of formal group law, so which means that that exists a commutative ring L, and so you have this ring homomorphism to R such that so we get the formal group laws. So these are our formal group laws. So it's the universal form. So, and turns out, we'll see this later, that this L, this ring L that we have, so this is also the coefficient ring of mu. So okay, let me try to some motivation, which I bet is not needed. So yeah, so this is a coefficient ring of mu. Right. So yeah, this is something that Lurie also states, which I find useful. So we can think about getting so interested in getting cohomology theories. So naturally we think that we would want, because there's a coefficient ring of mu, and because we have this universal kind of a property, that we may want this to right, to be cohomology theory, right? That works, right? But the thing is that so there are a few there are a few conditions that we need, and this does not always work. So there's this Landweber's theorem. Right? So Landweber theorem is basically, so okay, let me just briefly talk about it. So, so you have this map, right? So okay, maybe okay, we will get into that later, but maybe yeah. So you have this map of affine schemes. Right. So the thing is that this map, so the fact that so this formal group law associated to cohomology theory, so that also depends on the choice of complex orientation. So that is the deal, right? So yeah, more detail we'll get into more details later. So again, so just because it's motivation, just because we're motivated things. So the deal is that so the structure of the stable homotopy category. So first, okay, let me say this. So we are interested in this moduli space. Right. This is the modular space that we're interested in, of formal group laws. But they have to be in this. Right. So the quotient. Oops, wait, sorry. Yeah, the quotient. So Grisha talked about this. So this is the moduli stack of formal groups. Grisha talked about it in the second talk. So the deal is that we are thinking of the structure of the stable homotopy category to be related to the geometry of this this algebraic stack, right? So these are the basic premises. So now, okay, so now let's begin. So now I'll kind of briefly define formal group laws. Okay, so yeah, a lot of things are assumed, so I won't be defining everything. Right. So an even periodic cohomology theory, right, with the coordinate gives rise to the formal group law, right? So starting with the definition, a formal group law, which we assume to be one-dimensional and commutative always, over a ring is a power series. And satisfies the following. Right, so there are three conditions: symmetry, and the third one being associativity. Right. So, okay, starting off, well, maybe an example, a couple of examples actually. So the additive and multiplicative form of group laws. So like the basic example. So this is the additive form of group law, and we'll see how we'll see more. And this is the multiplicative form of group law. Right. Okay. Right. So first let's introduce a few things. So now, okay, so let's denote the subset of zeros. Okay. This. So it is the subset of formal string of our formal group laws over I. Right. So maybe remark. By substitution, we can see that if we have a map of commutative rings, so this is a map of commutative rings, so we have this induced map. Check this. Okay, so now we talk about the construction of the Lazard tree in detail. And I found that, and I mean, yeah, so it's pretty well laid out in Dewey's notes, but still we'll go through most of the details, at least in the for the Lazard's theorem. For the second part, maybe not so much, but for the first part, I mean, just to like reinforce things, we'll kind of follow along. We'll get into the details. So okay, so a general form of group law. So we have, so it looks something like this. Subject to some conditions, right? So subject to the axioms that we have. So okay, so for the first axiom, so how should it be? So let's do things. Let's get our hands dirty a bit. So this should be x. Whoops. Wait. Oh, sorry. So this should be equal to right. So this input, so we are getting something like this. So for the first condition. So for the first condition, we are getting something like this is equals to 1 if, sorry. This is equals to 1 if I is equals to 1 and 0. So CI 0, okay. C0 I is right and 0 otherwise. Right. And now from the second condition, so second condition is like, okay, so for the second condition, we want this to be equal to right. So from this we get right. So this is what we get. And for the third one, it gets a bit complicated. Like for the associativity one, we get a complex polynomial equations. Right. So okay. So let me formal group law is a map. So this is the way to think about it. So it's a map. Wait, I hope I'm not. Oh yeah, I'm messing up with the notations. Right. So to R, so this F, so this is the ideal of all these relations. Right? Relations and plus the associative. So for the time being, this is what we have. So this will be a Lazard string. So we define to be the Lazard string. We also denote this by L, which is L. Okay, right. So maybe a remark. So now if we, so by abuse of notation, if my AIJs are the images in L, I can see that, right. So this is a form of group law, which is universal. So this will be a universal. So what do I mean by that? That means that when I say universal, so this is a, so this will be an isomorphism. Right? So it sends a homomorphism to the push forward, right? So this has to be an isomorphism, and R is a commuted. Right? So that is what I mean when I say it's universal. So here's the claim. So the claim is that, so it's a created tree where these AIJs are degree y plus, sorry. Okay. So what do I mean? So say if x and y have degree -2, then f also has degree -2. So okay, maybe let me talk about this. Okay, so how do we think about it, right? So why do I have like this degree -2, for instance? So there's a way to think about it, about yeah, so let's not get into it. So let's assume this one for now. So okay, so now let me state. So this is the main theorem. This is the Lazard's theorem. So this is what I want to prove. So L is isomorphic to a polynomial ring where so each Ti has degree, right? So a corollary of this would be, so this is how, so we'll see how we can generate formal group laws, right? So how we can construct formal group laws by this result. So a consequence, so before proving that, a corollary would be, so we can get a formal group law from a sequence of elements in R. Right? From a sequence of elements in R. Right. So apart from the few examples, couple of examples that we have, so another example would be, so if F is a formal group law over R, and we have this polynomial, so by conjugation by G we get another form of group laws. The form of group law. So an important consequence, so another important example that we'll see that it plays a part in the proof. So using this and like other rotation form of group law, we'll see. So this means that for G, as we have defined G here, right? So for G, so we have this form of group law. So this is also a form of group law over this. Right. So this is classified by a map. So okay, let me get my names right. So okay, let me call this map as a theta. Okay, okay, maybe phi. Second. Yeah, I have this habit of stopping somewhere. I don't know. So maybe a bit confusing, but it doesn't stop. No, it does not have to have finite generators. So we'll see that this is an isomorphism of proof this. Okay, so we can check that this map is compatible with gradients, and yeah, this is yeah, an important thing. This is, so over Q it will be an isomorphism, right? Not over Z. Okay. So maybe a remark. So this map is a map of graded rings with degree to be true. If X has degree -2, then the X also has degree -4. Which the formal group law is to be used. Right. So now we get into the details of the proof stepwise. So now, okay, so So I is a ideal in L. The ideal given by all positively elements, right? And similarly, I dash. So ideal in the right given by all positive elements. Right, and I dash. So yeah, clearly, it's now that this map that we defined. Wait, we have yeah, so phi. So this map that we have. So clearly, so this maps I to I dash, right? And we have this induced map of created abilities, right? So now comes an important lemma. So let me put this down. So this plays an important role in the proof of Lazard's theorem, and we'll first state it and then look at a few consequences and go with the proof. So right, so for R and the map, so zero C is injective. And its images, so this map here. So this is induced by phi. Right. So right. And the image is like, so the image is like Z if n plus 1. So we will get to proof. And the PZ. N plus 1 is equals to B. Okay. The P is a primary. So okay, so some important consequences. So we'll look at some important consequences. So for all positive integers, and so this is isomorphic quotient, right? And okay, so this is one, and now, right? So this map that we have, so this is surjection right now. So we can so we can lift the generators, right? This is surjection, no, but it is a surjection. So we can lift the generators to Tn, right? So we'll get this map. So I'm calling this theta. Right. So yeah, another consequence is, so this is what I corollary. So this theta is surjective. So okay, it's maybe a quick proof. So this is just induction. So now we know this. Now that so this would be our inductive hypothesis, right? So theta is surjective. So remember, this is theta. So so this would be our inductive hypothesis. So this is in the image of theta. Right. Now, as so let me pause for a second. Okay, yeah. So now, as this image of theta, this image of theta is so it contains a generator. So it has a generator for this proof, and we know that this is much more. Say so. Yeah. So that will mean that it should also contain. Right. So this is the basic idea. So just induction. And now it's another corollary. Okay, so a lemma. So okay, so this map, so okay, for this, so we compose theta and phi. Okay, let me make sure again that yeah, so right. So this is injective. Particularly theta is injective. So okay, let's prove this. So okay, let's consider the square. So we have these square. Space. So this will be and this is theta equals to L and phi equals to Z. Right. It's a good proof, right? Now, so now we know that these two things are, so these are torsionary, right? So that means that these inclusions that we'll have, these inclusions would be injections, right? So because there's no torsion. And also, so this map that we have, this one right here, so this map is also injective, right? So thus it will follow that this bottom map that we have, the bottom map would also be injective, so that will mean that theta is injective. Right. Bottom map would be injective. So now we see these like these are like graded vector spaces with the same dimension, right? And yeah, right. So we'll just use previous lemma, and using that. So it just follows that this map would also be an a surjection. Right. So that just means that. So we have proved that the bottom map is an injection and this upper map is a surjection. So that will imply that this is a bijection. As an isometric. Right. So okay. So using this previous two lemmas, so here we got that this theta that we have, theta is injective, and in the this lemma we got that theta is surjective. So we got that theta is a bijection. Right? So that will imply Lazard's theorem. Right. So okay. So now we go ahead with the proof of this lemma star. So okay, let me write it again. So we want this to have this. Right. And so this is injective. So this is the theorem, and the image is Z if equals not equal to pk and pz. Okay, so right, so some notation. Let me introduce some notation. So we are interested in the subsets of some group laws over R such that, so this has degree -2. So, degree -2. So we denote this subset by GR. So by GR, so because like so there's this grading on right. So this is grading as we have this. Okay, why do we say GR? Because we have this, right? And so there are corresponding homomorphisms that preserve the grading. So that is the point. Like, to such subsets, right? Such elements, we have homomorphisms that preserve the grading. So that's why we have this GR substrate. Okay, right. So now, so some of your constructions, right? So now we are interested. So this is our, so we are interested in this, right? This is our object of interest. And we want, so this is what we want currently. A, so where A is an abelian group, right? So we construct so we construct string and so we define the operations. Again, I'm sorry. And then so let's give it a grading. So grading so that Z degree 0 and A degree 1. So this is the grading that we give. So then it will follow that. Yes, so then it will naturally follow that. So we have this important result. L oh sorry. Where is it? Saying dense. Right. So we get this functor. So okay, maybe F. Right. And now so we can just for this we just need the functor, right? Unida. And so if our group log over this ring would be, so how would it look like? So it would be a form. So this ring. Right, so satisfying the desired conditions, right? So this is how it will look like. So here's what we'll get. We will see that. So this is what we'll get, and so a few other conditions hold, and the following hold. So what are they? Say 0 and plus 1 must be. Yeah, this is just pretty straightforward. And this one may be not so straightforward, but so this is how we what we get. Okay, so we want to solve these equations. So all the equations that we have now. So now this homomorphism that we have, reducing the so you can write the name that we have. This graph here, so we call this phi. So phi. So this induces right. So that means that you get this is pretty bad notation. So I'm saying to it. So right now, so what does this mean? So an element A in A, okay, maybe pause for a second. Um, A is A is coming from, so we have a graded ring homomorphism. Right. Yeah, and so yeah, A is being okay, so maybe I can go on. I can take a second shot to drink water. All right. So we can assign. So yeah. Oh yeah. So there's. So we can assign to A such an right. Yeah, so this is a ring homomorphism, right? And similarly to G, you send G to GX. Right. So then G is sent to. So that should be what this. Right. Right now, and this ring that here, it is 0. So we can check this, and therefore we'll get. Again, I have to check this. Okay. Yeah. So the obvious solution to this would be like, so we're solving this. The obvious solution would be so you can set Aij and I and j both are non-zero, 0 and 1 of I and j are equal to 0. So this is an obvious solution to this equation, right? So like basically number theoretic stuff, right? And but you'll see that there are also other solutions which are like not so obvious, and they are divisible by this T, which is just like GCT. Right. So we want to figure this out. We want to see like what it is, right? We want to unwrap this. Now, okay. So a combinatorial result that is useful. So P is a prime, right? And suppose you have these P-based expansions, right, of RM and M. So then you have P. Okay. So an important corollary would be, so using this lemma, corollary, check this. Okay. Not P. So what does this mean? So intuitively speaking, so this means that some P digits of I is, so some P digit of I is larger than the corresponding P digit of I plus J, right? So another way of saying this is like, so I plus J in base P involves carrying, which is just a funny way to say this. It involves carrying. So, right. So a corollary to the previous lemma would be D. So this D that we have to find. Okay. Whoops. Right. So it's either a prime is a prime if n plus 1 is pk, and otherwise it's 0. It's okay. So let me prove this. So first we suppose that this is not equal to k. Then we can decompose it into, so okay, I'll just say this. We can decompose it as I plus j, right, non-trivial, such that the sum, we cannot calculate the sum without carry, right? So I'm just like, sketching the proof. I'm not writing it out completely. So that from that it will follow that P cannot divide this, right? And now if we set this to be equal to P bar K, so then we don't have such a decomposition, right? As I plus J, non-trivial decomposition. So that will mean that, that will imply that P is precisely equal to D. Right, so this is just a quick sketch. Now, okay, so now suppose zeta from A to A. So suppose it is a map for the obvious solutions of the equations, right? So we'll have such a factorization. See, where this lambda dash is a map for the non-obvious solutions, right? So now we can, so now the proposition that will necessarily prove this proposition, the lemma that we have, the star lemma. This one, right? So yeah, I'll give the proof of that, but that is basically the previous one. So it's outlined pretty neatly, details, including notes. So this is a isomorphism. Right, so this is basically the equality. This is what is needed. Right, so I see that I have almost 15 minutes left as per schedule, so I'll see. I'll try. So again, now coming on to the second part. So that proves, right? Because using the star lemma, we had proof. Professor, we can get to this again. So what we did here is like, so we had this lemma star that we call star, like this one, right? And using this as a consequence, we showed, I'll also take you to that slide. As a consequence, we showed that Lazard's theorem is a consequence of that lemma. Yeah, so this theta, we showed that it's a surjective, so this was the proof. And now, and again, we showed that it is injective, right? So it is a bijection. So that is how we got the proof of the Lazard's theorem as a corollary to this lemma. And after that, after looking at a few consequences, we proved the lemma. Right? So I claim that you can use this to prove. So the fact is this lambda dash is an isomorphism, and using this proposition, this can be proved that lemma stuff, right? So okay, so that was Lazard's theorem. So now let's begin with part 2 of the talk. So complex oriented cohomology theories. So starting with the definition. So a complex oriented cohomology theory, so I'm just trying to write everything short because I don't want to write everything, is a generalized cohomology theory. So suppose E, that's multiplicative. So first, so there is and that. And there is multiplicative and has a choice of some class for every complex vector bundle. So let's unwrap this a bit. So what do I mean by the second part? The fact that it has a choice of a thumb class for every complex vector bundle. So unwrapping it. So okay, so suppose right, so suppose we have a complex vector bundle, right, of dimension n. So this is a complex vector bundle of dimension n. So then we have a class. So we have this class such that, so it's the following. So you have the following. So these classes are natural under pullbacks. So what does that mean? So that means that if you have this map, it's a naturality, right? Natural under pullbacks. And secondly, so for all x and x, so the image of this side. So under the composition, so I'll write it. So under the composition is the canonical element. So what is the composition? So reduced versions. Right. So maybe a remark, or maybe I'll just say this. So if you have a complex vector bundle of, right, so if you have a complex vector bundle, we have a preferred orientation for this. Right, so for a complex vector bundle, right, we have a preferred orientation, right, and this map, so like the map that we have here, right, this map. So this one, so this one depends on the way these orientations match up, right? So for every complex vector bundle, so you have this preferred orientation, and so the maps, so they depend on the way the orientations match up. Right? So an example would be, so okay, I promised for an example and an example. So okay, one example. So the easiest one, singular cohomology. And okay, a non-example is not so straightforward, but it is actually straightforward. Seems not so. So non-example. So you just take real K theory. So if this is our size, the canonical line bundle. Over CPU. So we can prove that. So this is something that again I'm not like explicitly proving, but we can prove that. I'm just saying that you can. Oops. So there is a space. So this is, so you can prove that this is multiplication by 2. So 1 can never be there. So this is a non-example. Okay. So proposition. So every class, this is the infinite dimensional complex projective space, restricting to 1 under the following composite. So I'll draw the composite later. Extends uniquely to a complex orientation. So here's the composition. So okay, so now we okay. So now complex orientation. Let's see this now. Complex orientation in cohomology theory. So it gives rise to a Thormeisen theorem. So it's like this. Oh, sorry. Right. So okay, maybe a remark. So we also get these. We also get Chern classes. So I'll define. We'll also define Chern classes. So we also get Chern classes. So that we have naturality under pullbacks. I'll try to again. You know what I mean? And the other two foreign conditions. So and so this is the tautological line bundle over CP X, which is so what is the point of all this? So there is something that we see in singular cohomology, and we're interested about that for an arbitrary complex oriented cohomology theories. Right? So what am I saying? So you have understood right now what I mean. So So L1 and L2 are like bundles over by Z, right? So these are so this is what we're interested in. Now we know first when we're looking at singular homology, we have this nice right. So this is what we get when you're looking at singular homology. Yeah, singular homology. Right? Now, so you can also ask, I mean, can you do this for, as I said, can you do this, can you have a nice form for an arbitrary complex-oriented homology theory? So it turns out, again, I won't get into the detailed constructions, I'll just get into that. So this is just I'm saying, so. So where, so it's a form of, okay, so maybe, so maybe I'm trying to end this with a few computational results, right? So again, it won't be very detailed, just giving through them. So proposition. So E is a multiplicative cohomology theory. Right? And X is element restricted to. Right. So for all M, so we'll have this map. Right. And so it's easy to see now if we have this map, so then X into the M plus 1, so this maps to 0. So even hey, you can just see why this happens. So what is this, okay, right? So how do we see this? So xn plus 1, just write it. Okay, so okay, yeah, this is okay. So what are these VIs? So these are like so n plus 1 contractible sets covering V. So this would be equal to WC. So therefore, so because of that, so we'll have a map. And we can show that this map, in fact, is also an isomorphism. So, okay, so the proof involves, so is an iso. So this was our proposition. So I started here, and this is our proposition. So again, it will be just be a sketch. I mean, the other part of the proof is like details that I, being honest, would also like to like have not like worked out in entirety, but which almost obvious. So okay, so by the Amartya book spectral sequence, right? Using that, we get something like this. Just as using Amartya book spectral sequence. Right, so the E2 term is E2 term is an isomorphism, right? It's isomorphic to, sorry, it's isomorphic to and X and elements of, okay, so X and elements of stuff. all have like permanent cycles. So that means that there cannot be any differentials, and from there we can proceed to prove that it's isomorphism. So yeah, there's some complications. So another proposition. So you can want whoops. So again, I won't explain the proof more in details, but I'll just keep it through it. So for this, we'll use the Milner sequence. So yeah, there's this a lot of things that I'm just not saying. I'm just okay. So I think, yeah, I think it's worth just writing it down. So I want to find what this term is. Or this. I'm just using this. Oops, it's close to 0, right? So the right hand side will see. So this right hand term, rather. So this right hand term. So this term that we have. So that is just equal to. And this is something that we proved. Just proved. I mean, sorry. Yes. Yeah. I mean, not completely, but this is something that we did. So the right hand term would be. And the left hand term is 0. Yeah, I would get it y. So yeah. So right. So okay. So now let me define chart classes. Great. So maybe construction. So line bundle. So if we take a line bundle, so suppose from A to Z, so it is classified by this one, right? It's classified by this. So now suppose let's define. Right. And now, so suppose this map, we call it. So this classifies the universal line boundary, right? Suppose this classifies the universal line boundary. So what do we get? So from there we get so it is like so this is like you're sending X to X, right? So a form of the block. So from the universal example from this universal example that we saw, right? So we can easily prove this. Sure. This universal example that we saw just now. So this was our goal, right? Now, like the last thing, so we want to calculate. So instruction. So now again, so suppose this is a complex vector boundary. Again, dimension is n, and this is by this I denote the projective model of U. Psi, sorry. Again, using So again, using the TI-Schulz spectral sequence, we can prove the following. I won't give a proof. I'll just write it down. It's free. So this is the basis. Now, okay, now so there exist these unique elements, right? Such that this is where we define where our non-functional process comes. Right. And these so this R, so the ith Chern class of CI. So this is the way we define it. So we also, so I won't get into anything else. I mean, we could also have the notion of this like total Chern class. So I'm just writing this, just for completeness. So it's total Chern class. Right. So yeah, that's about it. And so maybe a few words. Say I'm already out of time, so just a few words that I'll say about complex Fordism. So just maybe peeping into the next talk. So it turns out we realized that MU is so it is the universal complex oriented cohomology theory. And the complex orientation on MU, so it defines a formal group law. Right. So we get this. Yes, I'll leave the other details so I'll leave it for the next stop and so this is the thing that you should have in your mind moving on to the next stop that can use the universal complex orientation and then so yeah, so maybe I'll stop here. Okay, let me stop the screen sharing. I think